Hydropower plants capture the energy of falling water to generate electricity. A turbine will convert the kinetic energy that comes from that falling water into mechanical energy, and then a generator basically serves the purpose of converting mechanical energy from the turbine into electrical energy. There are typically four components of any major hydropower project. One, you have the dam. As you can see here, the dam raises the water level of the river to kind of create this falling water phenomenon. It also helps control the flow of the water. The reservoir that will be formed then is in fact actually just stored energy. Then you have the turbine. The force of falling water pushing against the turbine's blades is what causes the turbine to spin. As mentioned, the turbine converts the kinetic energy of falling water into mechanical energy. Remember from before that energy can't be created or destroyed, it can just be converted. Then you have a generator. This is connected to the turbine by shafts and gears so that when the turbine spins, it causes the generator to spin also. This converts the mechanical energy from the turbine into electrical energy. Generators in hydropower plants work just like the generators in other types of power plants. You'll have it attached to transmission lines which transport the electricity from the hydropower plant to homes and businesses. And I should also clarify here that there is one alternative form of hydropower known as run-of-river hydro. This doesn't actually require a reservoir, and in run-of-river, it's the momentum of the entire stream that is flowing through the dam that actually drives the turbine. The reason we don't really focus on run-of-river in this course is because it is a small form of power generation, not used for industrial or large-scale residential use. So this graphic, and forgive me here, is going to seem a little daunting. We're going to talk about formulas for actually calculating the energy output from hydroelectricity, but it's important to kind of cover it, I think, in this class. So let me just pull the whole thing up here. Basically, you can calculate the power of a dam using the following formula. Power equals height of the dam times the river flow times efficiency of the turbine divided by 11.8. The amount of electricity a hydropower plant produces depends on two factors. Remember this, there's two factors that will determine exactly what your electricity output can be. One is how far the water falls, and the second is the amount of water falling. So on that very first point, the farther the water falls, the more power it has. Generally, the distance that the water falls depends on the size of the dam. The higher the dam, the farther the water falls, and the more power it produces. Scientists would say that the power of falling water is actually directly proportional to the distance it falls. In other words, water falling twice as fast has twice as much energy. The second point, the amount of water falling, is also pretty intuitive. More water falling through the turbine will produce more power. The amount of water available depends on the amount of water flowing down the river. Bigger rivers have much more flowing water and can produce more energy. Power is also directly proportional to river flow. So a river with twice the amount of flowing water as another river can produce twice as much energy. It's actually relatively easy to calculate the amount of power generated by a dam. And so I said this is daunting, but once we break it down, you'll see it's relatively simple. Power is equal to the height of the dam times river flow times efficiency divided by 11.8. So I'm going to use here just a small local hydro dam as an example project. Let's assume, and you can take out a pen and paper or type this on your computer, that the height of a dam is 10 feet. The river is flowing at 500 cubic feet per second, and it operates at about 80% efficiency. So power would be equal then to 10 feet times 500, which is the amount, the cubic feet per second for the water flow, times 0.8. Divide that all by 11.8, and that would equal 339 kilowatts. To get an idea of what 339 kilowatts represents, let's see how much electric energy we can make individually in a year. Since electric energy is normally measured in kilowatt hours, we would multiply the power from our dam by the number of hours in a year. So the electric energy from that dam is 339 kilowatts. We would times that by 24 hours per day times 365 days in a year, which would equal just shy of 3 million kilowatt hours. The average annual kind of residential energy use in the US is about 3,000 kilowatt hours per person. So we can figure out how many people our dam could serve by dividing the annual energy production by 3,000. So people served is equal to about 3 million kilowatt hours divided by 3,000 kilowatt hours per person. This dam, 10 feet in height, flowing at 500 cubic feet per second and at 80% efficiency, would provide enough energy for 990 people over a year. So our local irrigation or recreation dam could actually provide enough renewable energy to meet the residential needs of almost 1,000 people. So that's a good way of kind of understanding and grasping hydropower production. It is actually a very, very efficient form of energy production.